an example. So, in order to continue the proof of a theorem that I am proving, I need some general results concerning the uniformization of foliations. So here I will work in greater generality, so I will consider an arbitrary compact complex connected surface and an arbitrary foliation, singular foliation. So there are the leaves like this. And we would like to do the following construction. We take a transversal to a foliation, say a disk, a local transversal. So for every point, we have the leaf of a foliation passing through the point T. And we have its universal covering with base point T. Then we can take the union of this universal covering with T varying in the transversal. Let me call this UT. This is just the disjoint union. This. So this is a set. This set has a natural map P to the surface, which is just the tautological map which sends each fiber to the corresponding leaf. And this map, this set, has also a projection over T, which is the evident projection. And there is also a section of this projection, small pt, which is the section giving the base point in each fiber. Each fiber is the universal covering with a base point T, so there exists a distinguished point. So the picture is something like this. So this is a set. These are set maps. And we would like to give to UT the structure of a complex manifold in such a way that this PT is a holomorphic submersion. This is a holomorphic section. And this map to S is a locally biolomorphic map. So we want to construct this complex structure on UT. Now, it is very easy to give a topology on UT and to construct also a complex atlas, that is an atlas with holomorphic coordinate change, because so it is easy to give a topology to this space in such a way that P is a local homeomorphism. And so we can pull back the complex structure on S, and we get a complex structure on UT. However, this is not yet a complex manifold, because a complex manifold must be Hausdorff. So this is, in a trivial way, a possibly non-Hausdorff complex manifold, but we want that it is Hausdorff, because otherwise it becomes complicated. There is, in fact, a classical fact. showing that, so the problem is basically a topological problem. We want that this set with its natural topology is Hausdorff, and it is a classical fact that this is equivalent to the absence of vanishing cycles in the foliation. A vanishing cycle is something like this. A vanishing cycle in a leaf is a cycle. A cycle means a circle, possibly non-embedded. A vanishing cycle is a real cycle in a leaf, say L0, which is not homotopic to 0 in the leaf, but which can be approximated by other cycles in nearby leaves, which are homotopic to 0 in the leaves LT. So here the picture, this is a cycle which is not homotopic to 0, but it can be approximated by this cycle which is homotopic to 0. So it is a quite easy fact to see that the absence of these things is equivalent to the Hausdorfficity of this set, and hence to the fact that it is a complex manifold. No. This is the holonomy covering rather than... He considers the holonomy covering, I think. Yes, yes. No, but this is a very old, I think it is a Reb or... No. So, sorry?
What did you say?
No, this is a very old fact. And it is, I think that the Reb did know this. So the Reb component is the typical example of a foliation with a vanishing cycle. So the problem is vanishing cycles. Now, this construction concerning this, I call these manifolds covering tubes, if it exists, say. This construction was, in fact, introduced, at least in the context of holomorphic foliation by curves. It was introduced by Ilyashenko a long time ago, something like 69. And Ilyashenko considered foliations on Stein manifolds. And Ilyashenko proved that on Stein manifolds, there are no vanishing cycles. So this construction can be done. And moreover, Ilyashenko proved some important properties of this UT, namely proved that it is a Stein, when the ambient manifold is a Stein. But here we are interested more in the case when S is not, in fact, S is a compact surface, so it is, in some sense, the opposite to Stein. So, in general, if
it were Keller, you would prove easily that there are no.
If
it were Keller, you would prove easily that there are no vanishing cycles.
Modulo something that I will explain now, but yes, basically yes. So let me explain. There are basically two types of vanishing cycles. A first class of vanishing cycles, I will not give a precise definition, but let me call these analytic or algebraic vanishing cycles. So I give just an example. You take a foliation. For instance, the horizontal foliation on C2. You take a regular point and you blow up the point. So, This is the blown up foliation. And this foliation has a vanishing cycle. Because you see that if you take a cycle here, so this is a singular point, so it is not in the leaf. If you take here this cycle, this is not homotopic to 0 in the leaf, but this cycle can be deformed in nearby leaves to cycles which are homotopic to 0. So this is a vanishing cycle which is associated to a rational curve in some sense. There is the raison d'être of this vanishing cycle is that the foliation has an invariant rational curve with some special properties. But there are also worst vanishing cycles, which I could call transcendental. Which is basically, for instance, the Reb component. Now, the Reb component in the context of holomorphic foliation is the following. You take C2 minus the origin, take C2 minus the origin, so this is the origin, and take the horizontal foliation. And then take the quotient of this by a contraction, say by the standard contraction or a dilatation. So this is a compact surface, Hopf surface. And this contraction preserves the foliation, so there is a foliation on the quotient. This foliation on the quotient has an elliptic leaf, which comes from this. This is a leaf isomorphic to C star, because the origin is not here. And when we pass to the quotient, this becomes an elliptic leaf. And all the other leaves in the quotient are entire leaves, isomorphic to C, which accumulates to this elliptic leaf. Here again, we have a vanishing cycle. This is very clear in this picture because, again, this is a cycle not homotopic to 0, but which can be deformed in this way. And the same can be seen here. So we see here a cycle in the elliptic leaf, which is not homotopic to 0, but which can be deformed to nearby leaves in such a way that it becomes homotopic to 0. Now, this is a situation worse than this one. Here we see that the cycle is not associated to rational curves, like in this case. From a more technical point of view, in this case, if you take the nearby cycles, if they get closer to the vanishing cycle, these disks, we have a sequence of disks, and this sequence of disks has bounded area. And this is the reason why this sequence of disks converge to something good. In this case, on the contrary, if you take this sequence of disks approaching the vanishing cycle, the area is divergent. Now there is so since we want to construct these covering tubes, we have in some sense to eliminate vanishing cycles. And there is a very simple way to eliminate this type of vanishing cycles, changing a little the birational class of the foliation. So let me give a definition. I say that a foliation f is relatively minimal if there does not exist a rational curve let's call C in the surface S, which is F invariant by the foliation, and the self-intersection is negative, and the canonical bundle of the foliation is negative on C. It is easy to see that such a curve is necessarily a smooth rational curve. So it is invariant, and the foliation contains only one singular point of multiplicity 1. And it is a singular point given in a local coordinate by something like, with a holomorphic first integral of this type, where M is the opposite of a self-intersection. This is an easy exercise with the usual formulae. For instance, in this foliation, it is not relatively minimal, because when we blow up the point, we have created exactly a smooth rational curve with these properties. Now, if a foliation is relatively minimal, this is good. Suppose now that the foliation is not relatively minimal. Then we can, since the C square is negative, we can collapse this curve to one point. This is just the beginning of minimal model theory for foliations. We can contract, so if there exists, if a foliation is not relatively minimal, there exists such a curve, and we can contract the curve to one point. Now, if M here is equal to -1, when we contract the curve, we get a smooth point of a surface, and also the foliation becomes a regular foliation. It is exactly the opposite of this operation. If M is greater than 1, when we collapse the curve, we get, in fact, a singularity of the surface, which is of special type. It is a quotient singularity. And still, the foliation around this singular point is not singular, in the sense that the foliation is the quotient of a regular foliation. Now, such a situation is as good as in the smooth case. One has just to change a little the language and to use some orbifold terminology and things like that, or two categories terminology, or stacks terminology, as you prefer. So if a foliation is not relatively minimal, anyway, we find such a curve and we collapse it, and then we continue like this until we get a foliation which is relatively minimal, which will be perhaps defined on a foliation, on a surface with quotient singularity, but this is not. Yes, yes. An orbifold, and the foliation at the orbifold point is a quotient of a regular foliation. So the conclusion is that given any surface, any foliated surface, we can always do a sequence of contraction so that the final result will be relatively minimal. Now, it turns out that this operation, when the foliation is relatively minimal, vanishing cycles of a first type, vanishing cycle of algebraic or analytic type, does not exist. And so, we are, but there are again the transcendental ones. Now, in the Keller case, for instance, one can prove that transcendental vanishing cycles do not exist. So in the Keller case, in fact, it is always possible to construct these covering tubes. In the non-Keller case, this is not true. In fact, I gave the example of op surfaces, where there is a transcendental vanishing cycle.
In the Keller case, just the volume estimate.
Yes, yes, but there is yes. No, but no. Yes, you have a bound on the areas, so the limit will be a disk plus some rational cards, but among the rational cards there is one of these. In the non-Keller case, this does not work, but still there exists a theorem. So I give another definition to a relatively minimal foliation is uniformizable if, say, there are no vanishing cycles, or if the covering tube exists as a Hausdorff space for every transversal. And the good fact is that non-uniformizable foliations are completely classified. You know? The only relatively minimal non-uniformizable foliations are the so-called straight foliations on Kato and op surfaces. So an example of a straight foliation is the example that I gave here on op surface. There are other examples on Kato surfaces. In fact, most of the foliation on Kato surfaces are not uniformizable.
What do you call, what is the meaning of uniformizable?
It means that there are no vanishing cycles. So that the covering tube exists as a Hausdorff complex manifold for every T. So there are few examples, and in fact there are no more. Now, from the point of view of the theorem, the main theorem that I will prove, this means that in that theorem we may suppose from now on that the foliation is uniformizable. Because if it is not uniformizable, we already have the conclusion. So I cannot give the proof of this theorem, which is quite long, and so, but it is a fact. So consider now a relatively minimal foliation, which is uniformizable. So by this theorem, this is no loss of generality. So we have this covering tube with this locally biholomorphic map to S, this projection, and so on, which is H2. But that in the Stein case, the foliation is always uniformizable, and moreover, the tubes in that case are Stein. And of course, in the Stein case, one can use very strongly the fact that UT is a Riemann domain over a Stein manifold, and for Riemann domain over Stein manifold, there are classical theorems saying that under some there are criteria to establish that some Riemann domain is a Stein. But here S is a compact surface, and moreover, non-Kähler perhaps. So it is a problem. In the Kähler case, for instance, one can prove that the covering tubes are actually Stein. But I want to consider the non-Kähler case, of course. So the question is this object Stein? The fibers of the tube, so there is this vibration. The fibers are simply connected curves, so a submersion, yes, not locally trivial, of course. The fibers are simply connected, so disk by Schwarz-Köbe uniformization theory. The fibers are ATAR disks, ATAR C, or CP1. But in fact, CP1 does not appear because if you have a rational leaf, then by red stability theorem, the foliation is a rational vibration, not very interesting. And of course, we may have a mixing of these fibers. So this is the tube, and perhaps there are some fibers which are disk and some other which are parabolic. Now, I would like that UT is Stein for the following reason. There are two classical and very beautiful results by Nishino and Yamaguchi. Nishino theorems says that, so suppose that we have a surface with a submersion over the disk, such that all the fibers are isomorphic to C. And suppose that the surface is a Stein. Then the surface is a product. So this is under the if Pt minus is isomorphic to C, then UT is a product, biolomorphically equivalent to a product. Under the assumption if UT is a Stein. Yamaguchi theorems concern the case when some fiber is hyperbolic. Now, if some fiber is hyperbolic, we can put on each fiber the Poincare metric. More precisely, on hyperbolic fibers, the usual Poincare metric, and on parabolic fibers, the zero metric. Of course, if all the fibers are C, this is just the identically zero metric, but if there exists at least one hyperbolic fiber, this is a non-trivial metric. So this is this leaf fiber-wise Poincare metric on the fiber, can be seen as an Hermitian metric on the relative canonical bundle of the foliation, of the vibration. Okay, how to call this? This is something like this. This is just the canonical bundle of the vibration. And the Poincare metric can be seen as a metric on this line bundle. And this metric is a curvature. And the Yamaguchi theorem says that this curvature is possibly singular, but it is a closed positive current. So this means, if you want a more explicit statement, this means that you have this vibration. We can take some open set. And in this open set, you can take a holomorphic vector field, which is tangent to the fibers and non-vanishing. And then, so this is a vector field. At each point, we have a vector field tangent to the fiber, and we can consider the Poincare metric, the Poincare norm. We can take the log. This is a function defined in this open set. And this statement is equivalent to say that this function is plurisubharmonic. It is a plurisubharmonic function whose poles are the parabolic leaves, precisely the parabolic leaves. So this, a first consequence of this fact is that if ut is a Stein and if there exists at least one hyperbolic fiber, then the parabolic fibers correspond to the poles of a plurisubharmonic function. So they are a complete pluripolar subset, so a small subset. Now, this theorem of, so these are just abstract theorems about surface, Stein surfaces fibered over the disk. Of course, we can return to a foliation. So take a foliation, relatively minimal and uniformizable. And suppose that every covering cube associated to a foliation is a Stein. Suppose that is Stein for every T. Then we apply this result, for instance. On the leaves of a foliation, we can put again the Poincare metric. Again, on hyperbolic leaves, the usual Poincare metric and the zero metric on the others. And since the Poincare metric is functorial by covering, essentially, we can apply this theorem. So the consequence is that I write the same thing, the Poincare, the leaf-wise Poincare metric defines on the canonical bundle of a foliation a metric, an Hermitian metric, whose curvature is a closed positive current. If there exists at least one hyperbolic leaf. So, Professor Pereira talking this morning about positivity property of a canonical bundle of the foliations, Miyaoka, McQuillan, Bogomolov theorems, and things like that. This is, in some sense, the analytic counterpart of that result. It says that, well, under this assumption, but I will discuss later this assumption, if there exists at least one hyperbolic leaf, the canonical bundle is a so-called pseudo-effective line bundle. It has a metric with a positive curvature in the sense of currents. Now, the assumption that there is the assumption that UT is a Stein. No? Yes, yes. How to prove that property? Unfortunately, I am unable to prove this in a very full generality. But there is a sample case which can be done, which is the following. So, proposition. Suppose that this line bundle. So suppose that the relative canonical bundle of the tube is holomorphically trivial. Remark that for evident reasons, this is always a topologically trivial line bundle. And if UT is a Stein, then it is holomorphically trivial. Now, conversely, suppose that UT is holomorphically trivial. Then UT is Stein. The proof of this fact is not very complicated, actually, because the proof is the following. Suppose that this relative canonical bundle is holomorphically trivial. It means that there exists a section which is nowhere vanishing. So call beta this section. Nowhere vanishing. So this means, more concretely, that on each fiber, we have a holomorphic one form without zeros, and this family of holomorphic one forms is holomorphic. Now, every such one form on every fiber can be integrated. It is the differential of a function, because the fiber is simply connected. And this function is uniquely defined if we impose that it is 0 on the canonical section. So by integrating this leaf-wise or fiber-wise one form, we get a holomorphic function. A holomorphic function which is an immersion on each fiber. A holomorphic function, let me call an integral of beta. So we have a holomorphic function which is an immersion on each fiber. And we have also the projection to T. So let me call PT. So we have finally a map to C2, which is a locally biholomorphic map. So this means that thanks to this assumption, our tube, our covering tube, it is not just a Riemann domain over S, which is an object difficult to study, but it is also a Riemann domain over C2. Now, as I said in the case of Ilyashenko theorem, it is much easier to deal with Riemann domains over C2. In particular, if you want to prove that the Riemann domain over C2 is Stein, it is sufficient by Occa's theorem to prove that it is orthogonal convex. So it is sufficient to prove that if you take an embedding of an orthogonal figure here, then this orthogonal figure, this embedding can be extended to an embedding of a B-disk. This is orthogonal convexity, and in the case of Riemann domains over C2, this is equivalent to the Steiners. This is far from equivalent to Steiners for a Riemann domain on arbitrary surfaces. So to prove the proposition, one has simply to prove the orthogonal convexity. And this can be done. You take an orthogonal figure and you extend. It requires 2 pages, but it is not very common. It can be done. Continuity methods and things like that. So this means that, for instance, this result holds under the assumption that every canonical bundle is holomorphically trivial. So this is the general theory. Now I return to the particular theory, to the example. And so let me recall some things that I already did. So there is a Telemann cycle. I return to the situation of yesterday. So we have our surface of class 7, 0, 2 with a foliation. There is a Telemann cycle. There is the Telemann cycle is invariant by the foliation, and we have so we have one singularity which is here and a second one. Now let me consider the case in which the second singularity is on the curve. It is one of the 2 cases that I discussed. And I use this theorem to... so let me consider this case. I will complete the proof in this case. So in this case, we have also that Kf is numerically equivalent. Let me say, yes, numerically equivalent to O of minus C. And recall also that C squared is equal to minus 1. So I showed this yesterday. Now, we may suppose that this foliation is is relatively minimal. Because if it is not relatively minimal, it means that there exists a rational curve with the usual properties. And these rational curves, of course, it cannot be the curve, the Telemann cycle. It is necessarily a curve like this. It is a curve which contains a singularity, only one, and it must be this. And so we are done. We have founded the second rational curve. So this, in fact, in this case, the second rational curve exists for non-relative minimality reasons. So suppose now, by contradiction, if you want, suppose now that the foliation is relatively minimal. We may also suppose that the foliation is uniformizable. Otherwise, we have the theorem of classification, which already did the job. And in order to apply this type of results, I have to show that the canonical bundle, the relative canonical bundle, is trivial. Now, we have ut to S, and we have the universal covering like this. Now, as I explained yesterday, if the canonical bundle is, for instance, numerically trivial, it means that it is trivial when we pass to the universal covering, and we have a holomorphic vector field generating the foliation. Here we have this fact, so this means, so perhaps it is better to write like this, flat. So when we pass to the universal covering, this line bundle becomes flat, becomes trivial. And this means that on the universal cover, the foliation is generated by a holomorphic vector field, which vanishes on the curve C, on the cycle C tilde, the pullback of C. So we have here a holomorphic vector field which vanishes along this infinite chain, and this vector field can be pulled back to the covering tube, because this is a local biholomorphism. So we get on the covering tube some holomorphic vector field, which is vertical, and which vanishes only on those fibers which correspond to this infinite chain. So if you take, of course, if you take a transversal like this vector field vanishes nowhere. If I take a transversal like this, there will be some fiber over which this vector field vanishes. But if it is the case, we can simply multiply this vector field by a function with a pole on this line, on this fiber, by pulling back a function below. So in any case, we get that a holomorphic vector field nowhere vanishing. And so we get the hypothesis of triviality. So I can apply all the general theory. Now I claim also that there exists an hyperbolic leaf. This is clear. So here we have a leaf which is C minus the 2 points P and Q. So this is isomorphic to CP1 minus 3 points. And it is hyperbolic. So by that theorem, we can put on the leaves of the foliation the Poincare metric, and we get that the curvature of this metric is a closed positive current. Omega. And as I said before, so this means that the canonical bundle of a foliation is a so-called pseudo-effective line bundle. Now I use a very remarkable and special properties of non-Kähler surfaces. So the property is that if you take on a class 7 surface a pseudo-effective line bundle, then it is numerically equivalent to an effective one. In other words, I can write this pseudo-effective line bundle as some effective one modulo a flat line bundle. So flat, effective. This is a special properties of non-Kähler surfaces. Of course, it is not true on projective surfaces or things like that. But this is here one of the few points where non-Kählerianity is a good thing. It is an advantage. Now, suppose that, so by contradiction, I suppose that C is the only curve on the surface. Otherwise, there is a second curve and we are done. So if C is the only curve, this effective line bundle is necessarily of the type proportional to C, where alpha is some non-negative constant. In fact, this equality must be understood in the sense of peak tensor Q. It is an equivalence of up to taking some power or with rational coefficients. So finally, we get that Kf is numerically equivalent to alpha C for some alpha non-negative. On the other hand, we know that Kf is numerically equivalent to O minus C. So we get that C is numerically equivalent to 0. But C square is equal to 0. It is equal to minus 1. And of course, this is a contradiction. And so this contradiction completes the proof. In that case, I remark that here I use a contradiction proof because after the theorem has been proved, so we have this rational curve like this. On this Kato surface, we have a unique foliation. And that unique foliation is not uniformizable, and it is not relatively minimal. So there is the second case, which is the more complicated, in which the second singularity is outside the curve C. And in that case, the foliations on that Kato surfaces are relatively minimal and are uniformizable. So in that case, I will not use a contradiction proof. So it will be more complicated, and as I said yesterday, one has to show some completeness of some vector field and things like that. So I will prove the second case tomorrow, but still these results about uniformization will be the central step. Let me just remark to conclude that here I have used this argument of lifting to the universal covering to show that the hypothesis of triviality of the relative canonical bundle is satisfied. Exactly the same proof, even simpler, works in the other case. Because in that case, we also have, even better, we have that this is flat. So again, when we pass to the universal covering, it is a trivial, and so here we have a holomorphic vector field generating the foliation, which can be lifted on the covering tool. So also in that second case, I will use this type of results about basically Yamaguchi and the Nishino result. So I stop here because it is better.